Good afternoon, it's me again, Jean-Louis Van Bella. I wanted to maybe start a bit of a new series of videos which are a bit more advanced in terms of the math. You will need to understand them, but which also show that yeah, I do understand mainstream physics. It's just that, I have more conservative ideas about what makes sense and what doesn't make sense. Last time I think I ended with this slide, and I said, I started reading or rereading Gauge Theories in Particle Physics. It's a great book. It's not online, not like Feynman lectures, so you have to buy it. I warmly recommend it. I got put off by it because of the first chapter, where they basically start with Yukawa's theory of strong interactions between a proton and a neutron, which would explain why positively charged proton and neutron that has no charge would stick together. The key idea would be that there's some kind of new force. I sort of demolished that idea in my previous videos, just like that in that instinct in mind that says that weak theories, weak forces, weak interaction. A force needs to explain why things pull things apart, or why they come together. A disintegration of a particle is going from an equilibrium to a disequilibrium state. And I think classical physics must be at work to explain why we go from one stable state of affairs through a number of disequilibrium interactions to a stable state again. I'm not going to dwell on that, because the idea here is to talk about this book and basically quantum electrodynamics, and in particular about why I think quantum electrodynamics makes sense, and why quantum chromodynamics and other quantum theories might not make sense. And I'm gonna do it through a bit of a new angle. Gauge Theories in Particle Physics is the name of the book. So I'm gonna explain what a gauge basically is, and how it works in quantum electrodynamics. So electromagnetism as a gauge theory. In the papers that you have on my ResearchGate page, I will show a few at the end of this lecture. That we have Maxwell's equations, which work fine. But we're talking about charge densities rather than individual charges, point-like charges. And so that's where quantum mechanics comes in, the Planck-Einstein relation, which basically says if you think about particles, think of my interpretation of it, think of particles having a structure, think of them as being charged oscillations. And so then you can, that's the idea behind the Broy's matter wave. And I said at the end of the lecture, I'm going to show my interpretation a bit of the Broy's matter wave. Said I think the breakthrough there was that we left a bit the idea of a charged particle for a mere naked charge, and then we think about the equations of motions, or the equations of motion as Dirac put it in his Principles of Quantum Mechanics. And we try to develop wave equations for that and find solutions, and these solutions are wave functions. And for me, wave functions model something very real, and indeed they are the equations of motion of the naked charge, and that motion in turn generates an electromagnetic field, and you have that interaction, and so everything comes together beautifully. But so to go back to the Maxwell's equations, I have them here in their sort of a classical expression where we have where we don't use natural units. We have the electric constant, c square, c, we can bring it to the other side, and we have the magnetic constant. So we look at that in the normal SI system of units. if you look at these equations, you have Gauss law, here, divergence, sort of a flux, modeling the source of a field, and so the source is generated by a charge density that can be infinitesimally small, or we can also think of integrating it over some kind of arbitrarily small or large volume of space. We have Faraday's law, or the Faraday-Lenz law, that in changing magnetic field will cause some circulation of the electric field. Divergence of B is zero. That means basically we have electric charges but no magnetic charges, and that's why also I'm very skeptical of gluon or coral charges. The only charges we can see in nature that we can really measure and prove is the electric charge. And then we have this very special equation on the circulation of the magnetic field. We have Ampere's law, basically a current. Current generates a magnetic field around it. And then we have this second term, which must be there because of the charge conservation law. A current will cause locally a decrease in the charge in a certain area, and so it must have an effect on the electric field vector. I'm not going to talk about that too much. That's standard electromagnetism. Moving to natural units or electromagnetic units, in Hey, actually, it's the first time I see in a good physics book. So a really nice explanation how natural units must be used. You cannot just do what you want. But if you use the so-called Heaviside Lorentz units with the standard convention that we will also want, h bar, Planck's reduced quantum of action, and the light speed be equal to 1, then you can rewrite these equations in a much simpler form. You can see the electric constant disappears, the c squares disappear, and that's basically it. For the rest, they stay just the same. But using these ones is often a little bit easier for the kind of mathematical treatment I'm gonna give you now. Maybe very quickly on natural units, because I like that, and I know it's kind of confusing. I don't like them, but how does it work really? Like when you want to put the electric constant, when you want to say I want to equal its numerical value to 1, I want to set it to unity. We know that its physical dimension is the Coulomb charge squared times the time unit squared times the mass unit. Mass and force are related to Newton's first law, right? And then we have the cube of the distance unit. Very complicated thing, but when you think about Coulomb's law, where you say basically the electrostatic force is the product, its strength is the product of the two charges divided by the square of the distance time this I would say proportionality constant, then it comes out all right, and you can see that this constant of proportionality must have the kg must have this physical dimension, because here we have two charges, so we have a c squared, r square, and the distance. So basically you must have something, the electric constant there, with, let me clean up my sheet, how it works, which has that physical dimension to make the units come around, because we measure force in Newton. So we can say, let's start with the simple thing where we say, look, the absolute velocity of light, c, we want to set that equal to unity. Then we have a choice. We know that it's a velocity, so it's a product of its dimension is meter divided by seconds. So we must choose the right, put it between brackets, because we have a choice, time and distance units. An easy one would be to use like light seconds for the distance unit. Then we say, okay, our unit of distance is the distance that a photon travels during 1 second, and then it's equal to a unity. But we could choose others. We could choose a shorter time unit also, much smaller one that is more like in tune with the huge frequencies at the subatomic level, and etc. So it's not enough to say like, okay, C is 1 and we have a system of natural units. No. So we also need to use other equations in physics to reduce that degree of freedom. So it's say, okay, what time and what distance unit are we going to choose? So we could think of the definition of Planck's quantum of action. That's another constant in nature, and we could say, well, we're also going to put that equal to 1, and then probably we will not have the problem of a choice anymore. The problem is the physical dimension is Newton times meter second, so we can immediately see if we want to put Planck's quantum of action in its reduced form here equal to 1, then we do not only have to make a choice for the time and distance unit, but also for the force unit, some kind of natural force unit. I put that here, that's sort of confusion. If you choose a new force unit, of course, then you also have a new mass unit. The definition of mass, what is mass in nature, is, it's the inertia to change in the state of motion of an object. So the mass is nothing more, nothing left on that. If you, and how does it change? The state of motion of an object change? It changes because you exert a force on it. So you have Newton's force law. 1 Newton, the units is 1 kg by 1 meter divided by 1 second square. I made a mistake here. A Newton is a force of 1 Newton is something that gives a mass of 1 kg, an acceleration of 1 meter per second per second. So sorry for the mistake here. I'll quickly correct that. There we go. So we got 2 equations now. H is 1 and C is 1, but we have a new unit, the force, which we have distance, time, and force mass, which are related. So we need a third equation, I would say, or a third constant of nature, definition of a constant of nature, and that's the one which we have here. A candidate is the electric constant, and that's equal to 1. Now we're again in a problem because, I said here dimension does not only have mass, distance and time, but also the charge. So we must now define a natural unit of charge to set C equal to 1, H bar equal to 1, and epsilon naught equal to 1. So that's then where we can use the magnetic constant, because we also know its unit is, it will have coulombs, kgs, meters, seconds, while the time units then. But we have that, and we know that the square of the speed of light is equal to the inverse of the product of the magnetic and electric constant. So then we are finally in a system where we have natural units, where a number of, the important constants of nature, electric magnetic constant, and Planck's quantum of action and the speed of light, all these fundamental constants are equal to unity in a revised system of units, natural units. Okay, I didn't want to talk about that, but it's good. Back to Aitchison Hay's gauge particles. Aitchison Hey in the second and third chapter, where they want to show how wave equations are basically compatible with classical electromagnetic theory. Start with the mentioning the charge conservation law, which you can express in 2 ways. Either locally charge gets conserved, divergence of the current vector is minus the time rate of change of the charge density, and as said, you can integrate over any arbitrary volume in space V, small, large, and put the same thing. We integrate that divergence over the volume of space, and it must be equal to minus the time rate of change of the charge density in an infinitesimally small volume within that volume V. So I think we can appreciate now why this charge conservation law. And that's a bit the question is. Okay, that's there, and that's when you do particle physics and your particle reactions, and you think about the charge conservation law, you have basically two approaches. This what I call rather simplistic co-determination of charge of, say, some kind of stable or unstable particle, let's say. It must have a charge because in the reaction we have two known particles coming in, A and B, and we see two other known particles in the sense that their charges are known, and we know that the charge of X will then be determined by the charges of A and B and C and D, because the charge at both sides in the equation must be equal. So the question that Aitchison and Hey ask, rightly, as quantum physicists, is that auxiliary. We could also check, and ideally we should have the same result to see, when we put this unknown particle X in known electromagnetic fields, we can determine its charge. That's what happens in bubble chambers and all that. So this uses dynamics, and that's easily said and a very simple idea, but how does it work exactly? So, and they immediately put the rather critical remark here, which I found remarkable for, mainstream quantum physicists, and I really like it. They say conservation laws, which you will have heard, like lepton and baryon number conservation, they have no dynamical counterpart. As far as we know, there is no leptonic or baryonic force field. And that's sort of the criticism I have of these new theories, and quark and gluon. Also, we don't have color fields or other stuff. According to some mainstream theorists, we have. But they know that because we don't have like a good dynamical theory, it's kind of normal that baryon number conservation is we see it in a lot of instances, but it's not absolutely conserved. And a number of the very new to unified gauge theory says that for the strong and weak and electromagnetic interactions, the three theories, the standard model, they probably need to pay more attention and have a unified dynamical theory to explain. Let me put that a bit in the math. I said gauge theories. That's 70s, 80s, 90s, what people were looking for, new gauge theories for the non-classical sectors, I would say, in the standard model. The electro-weak or the weak force, the strong force. So let me remind you in classical electromagnetic theory what a gauge is and why we have this particularity that it's actually invariant of the choice of a gauge, although I did talk, and I will talk again about a suitable choice of a gauge to put Maxwell's equations in a particular beautiful form. Let me remind you of this concept of the scalar and the vector potential. The scalar potential is like an easy one in electrostatics. It's the electrostatic potential, which we know very well, the Coulomb potential. With dynamics that changes, and I will show how. And then we have this vector potential, which is linked to the magnetic force. How exactly? We know there's no magnetic charge. There's no divergence of B. It's zero. So in plain mathematics, in vector algebra, we know that if the divergence of some vector field is zero, then B must be the curl of something. Curl is another vector field, of course. So B must be the curl of some vector field A. Which one? Well, we don't know. We actually have a choice. We will see that in a moment, and that has to do with the gauge. But we will refer, and that's the vector potential, to this new vector field as the vector potential. So that will be our first equation. The scalar potential. So it's just a familiar, I said, phi that you get from the electrostatic field and electrostatics. And you get the electric field vector from taking the the nabla, the vector operator, differential vector operator, to that static electro potential. In electrodynamics, however, when charges move, when we have changing fields, we have Faraday's law, and then we know that we cannot just say, okay, this is the static vector potential, and we take the gradient of it. Then we have an additional thing at play, and it is, well, there will be magnetic fields because there are moving charges, and so we'll have some circulations, some curl of E. So that gives us that extra expression where if we combine these two, because that's valid in any case, we have magnetic field. So in dynamics, we have B is the curl of some A. Delta A is minus delta B, so we replace it by that curl of A. So we get this expression. And that implies that this is another thing. I put the two main theorems here. The first one is, if you have an expression like this, the curl of some vector field is 0, then there must be some scalar field, psi, I put it here, such that A is equal to the gradient of that scalar field. So that's the first really theorem, mathematical theorem, not a physical one. If the divergence of some vector field D is 0, then there must be some vector field C, not a scalar field, such that D is equal to the curl of that vector field C. So now we're applying this one to that one. So E plus this complicated expression must be the gradient of something here. Sorry, it was that one that I'm applying to that situation. Okay, how are we gonna know that? And that's where this new symbol is chosen, V. It's a scalar potential. The V does not refer to a vector potential. It's also not the V you will see, I will talk about later in the electrostatic case for it's Aitchison Hey. They use the symbol nu V for the scalar potential, and I think it's a bit of confusing symbol because we think about maybe other things, but it's good. So we can write this. E is minus the gradient of that scalar potential minus the time rate of change. All right, the time rate of change of the vector potential. Yeah, that should work out when we apply this. Yeah. Just thinking. Yeah, okay, yeah. We get from this equation to that equation. There's no substitutions needed. We have E, and we just bring this one to the other side. So we have two equations now, this one and this one, and these two equations, 1 and 2, they actually are the solutions. I don't show that here, to equations 2 and 3 of, let me go back to them here, 2 and 3, these two equations, the Faraday lens equation, they're a solution. Now you will say, what is a solution to a set of equations? Do we have a definite? Do we have the initial condition? Well, no. We also have the two other equations, so we're not there yet. So basically, what we did, I know that here is that a bit more modestly than saying we have solutions, complete solutions, is that we rewrote equation 2 and 3 of Maxwell's equations as potential functions. What's the advantage, you will say? Well, we had with E and B, we have like 6 functions, and they're functions of space and time. We have the magnetic field vector, which depends on x, y, and z, and is also a function of t, each of these 3. And so E, I will show that in a moment. You have, it's pretty complicated, the E's and the B's. So now we only have 4 potential functions, which of course are a function of space and time as well, but it is a simplification mathematically, and that's of course because of the constraints that are implicit in equation 2 and 3 of Maxwell's equation. So we have this. B is the curl of the vector potential, and E is minus the gradient of the scalar potential minus the time rate of change of the vector potential. You will say that's quite a formidable, and you displace the problem because we still don't have A, and we still have and V. So how do we get these ones? And that's the thing where when you try to find solutions for some real or theoretical situation in which charges move around and fields change, you will find that, well, we have a choice for A and V. They are not uniquely determined, and they depend on what is referred to as a gauge. Here I will follow Feynman's argument I noted here, volume 2, lectures 14 and 18. They are online, you can look it up, where he shows that basically any A prime, call it A prime or A accent, which is equal to, you know, this solution, this vector potential we are looking, plus the gradient of some scalar field. Well, it will work as well as long as we also have another scalar potential, which will also be co-determined by this, you know, scalar field psi, and more in particular, this v prime will be equal to v minus minus the time rate of change of that scalar field. So that argument is there. I'm not going to repeat it, but he shows that yeah, we can have these A and V prime, and it will yield exactly the same physics, I would say, because the electric and magnetic field factors may say that they're not real and they appear differently in, you know, a moving reference frame or one that rotates and whatever. But the E and the B vectors are, of course, they model the physics of the situation. So they will yield the same physics. So how do we, you know, that seems too complicated. We thought we got something better, less functions to solve for with that scalar and vector potential, but you know, we get now an extra degree of freedom in the system. You know, these equations here imply that the gradient of psi, or is it phi? I always, but I think it's psi, is minus is a prime minus a, and minus delta. We can rewrite that as the difference between the two. The difference between this new scalar and vector potential that we would work with minus the original one. So the question really is, how do we choose then, or how do we get a psi? Can we eliminate it somehow? Yeah, we should eliminate. So, and that's what's called by choosing a gauge. You know, Feynman shows really that, you know, by adding this delta u, that's and that's how he eliminates it. He shows, and again, I'm not going to go into detail of the math, but you know, if you choose a sensible, what I could call a sensible expression for the divergence of A, then you know, it evaporates and you have a unique choice, and the equations reduce beautifully, and you can solve everything in terms of you know, the charges and the current. With static fields, you know, first half is we always had this implicit choice of the divergence of the. He did not make it explicit. Only in the last part he says, like, you know, the vector potential that is actually associated and comes out of these equations for electrostatics is such that the divergence of that field is equal to 0. For dynamics, we cannot do that. And again, I'm going to refer to Feynman. We take a rather special choice for the vector potential, such that the divergence of the vector potential is equal to minus 1 over c squared times the time rate of change of your very classical electrostatic potential phi. Again, I'm going to go quickly over that, but it yields, I said, very beautiful equations, sort of the equivalent of wave equations in electromagnetics. So we have wave equations for, like, you know, sound and the motion of air and gas. So here we have wave equations. You see, it's a squared a gradient vector, Laplacian, and And we can apply that to the vector n squared, and then we have this second degree time derivative, and indeed here you see the currents and the charge densities. So we have a solution based on, again, charge and current densities, and it models how things work and how the electric magnetic fields will work, because from the A and the phi, of course, we can derive backwards the electric and magnetic fields. So that's a total solution, but it was, let's say, it was dependent on choosing this gauge, a sensible expression for the divergence of the vector potential. So how does it work now in terms of quantum electrodynamics? I wanted to mention actually choosing this gauge. That's referred to as the Lorentz gauge. Now, there's a lot of confusion because it's Lorentz and not Lorentz with a T. Lorentz was a Danish physicist, and he found this thing quite early when he was looking for, nicer, more compact expressions for the electromagnetic theory. Lorentz with a T is, of course, the mentor of Einstein, Dutch physicist and Nobel Prize winner, etc., who also was the driving force behind the Solvay conference, Hendrik Andrik Lorentz, who died just before the war, unfortunately. Second World War. So they do not mention the Lorentz gauge, which we choose, which in volume 2 of Feynman's lectures is the gauge that is used throughout, but they immediately work, and that's what the beauty is about the generalization that they do with the general gauge invariant model for quantum electrodynamics. So in normal words, they show that Maxwell's equations remain invariant when you choose another gauge, or transform your gauge, as you call it, and how it works. So these new equations, which we will show now, also are very beautiful. I don't think they're as beautiful as Feynman's equations, but they are referred to as a gauge invariant or Lorentz with a T covariant field equations. The math is complicated and it's probably going to blast you away. So let's go through it fairly quickly. The starting point is indeed what we wrote a bit differently, is that we can choose another vector potential, an A prime, and from V that we had, if we had a given gauge, we can go to another one, and we know that to be consistent, that's sort of what is in all the things, that that new A prime will need to be the original vector field plus the gradient of some new scalar field, which that's a he. My Latin is not good. And the scalar potential V minus delta G over delta T, and that should work. We know that works in very simple, EMB terms. But of course, in math, we don't work in very simple EMB terms. We want simpler, smaller, so we will use full vector notation. We will write we will combine the scalar and the vector potential in a new 4 vector, as it's called, which is has 4 components: the scalar potential and then the 3 ax, y, z components of the vector potential. When we do that, we have a full vector. We will also define a sort of a new operator, which combines the time derivation minus the gradient, so spatial vector operator and 3-dimensional operator and 1-dimensional time derivative. So this operator is, like Jenkins said, hungry to operate on something, so we will let it operate here on this new scalar field He, and you can check it should work, because these 2 operators indeed operate on scalar fields, not on vector fields. And we have, of course, the old vector potential and the old scalar potential, and so we get this expression, basically these 2 expressions reduced to one one expression here, which is simpler or not. That depends on how familiar you are with 4 vectors. The funny thing is also, we talked about the charge conservation law. We can define a new 4 vector which combines charge density and currents, how currents flow in our system. And we have then a 4 vector. Let me clean up. It's a 4 vector, so I must remove the 3-dimensional arrow here. It's a 4 vector that's indicated by the mu, and it's in electromagnetic natural units. We don't have the electric constant here, so we have that. I'm not going to say too much, but it will pop up a little bit. This operator, you see, I put the mu downstairs, and yeah, there's a reason, because you can have this mu upstairs also here. I hope I got it right here. Yeah, where basically the time-space signature comes up here, and we can inverse it. And we have, I even don't know if it's time-space because there's only one space-time, and we can inverse it, but we can put here a minus or a plus. So we have a degree of freedom here, and that's sort of how this upstairs and downstairs notation works for the vector operator. I will show in a moment that it's not always that easy to interpret things in terms of, oh, this is downstairs, so there must be a minus sign in everything that follows after the first component. No. A particular thing to do with these downstairs and upstairs versions of a vector operator is that it's equal to this, it's not a delta, it's the D'Alembertian. And actually, I don't know, it's sort of a block or a house, or I should have looked it up on Wikipedia how you pronounce that. It's a D'Alembertian operator, and you can write it either as this, or with this square to emphasize that the downstairs and upstairs version of the simpler operator. Yeah, it's said it's not it's sort of a delta. Yeah. Equals the product of the downstairs version with the upstairs version, which has not a plus. So we have basically this the second degree second order derivative with regard to time minus the Laplacian, the second order spatial derivatives in all 3 dimensions of time, of space, sorry. Okay, maybe I lost you, but I think maybe not, when you're still here. We can now introduce really this highbrow math, as I'd call it, sort of to introduce how QED looks like as a gauge-invariant quantum field theory. So I said we have upstairs and downstairs versions of this operator. We also have it of the current vector, a 4-dimensional current vector, which I said combines charge and the currents in 3 dimensions, the real current, the charges that move through space. And we can have a plus and a minus sign. And here we actually see that in the notation of Aitchison Hey, the minus sign is actually in the upstairs version of the 4-vector. And I think it's got something to do because of the historical wrong convention in regards to currents. Currents model positive charges moving in space, while we know it's actually negative charge that moves from a positive to a negative space. I'm not expressing it in the right way, but you know what I mean. Engineers will know what I mean. So we can write on something like this. This is a 4-vector operator operating on the 4-vector current vector, I would say, but this which includes that these charge densities. And we can show that the upstairs version of the operator times the downstairs version of the current vector is equal to the downstairs version of the operator times the upstairs version. So that's a nice symmetry. I don't know what it means, I just put it there. But there's a lot of symmetries like that, and they're intimately related to the symmetry that is inherent not only in space-time in which things happen, but also how electromagnetics work. So now we're gonna introduce tensor algebra, and I'm not gonna repeat the argument of Aitchison Hey, which I refer to, page 46 in their first volume. They have a problem in which they work things out and an appendix, but basically they use and play with this electromagnetic tensor, or the field strength tensor as it's called. I'm just gonna write it out what it is. It is a matrix, and it is this matrix here. Zeros along the diagonal, and then we have the EX, EY, EZ above. We have the BX, YZ components arranged like this, and it's symmetric, anti-symmetric. The minus becomes a plus, and the minus becomes a plus here, and we have the C here if you normalize, but I don't do that here. But that's the matrix you get, and so this is called the electromagnetic tensor, and these little mu and V, I guess, are just indices here, and then they go from 0 to 1 to 2, 3 here, and from 0 to 1 to 2, 3 here. So for each mu and 0, you have a matrix element. So that's all fine. And the point is, if we do a gauge transformation, will this electromagnetic or field strength tensor, and I said I will let you look it up what it means. Will it change? Well, the thing is, we just said it shouldn't change. You know, the electric and magnetic fields are sort of the real thing, the real physics, and so they shouldn't change. So we must prove now that this electromagnetic field strength tensor doesn't change under a gauge transformation like the one we wrote. Well, the one we wrote, I have now a 4-vector which combines the scalar and vector potential. So this 4-vector primed must be the old 4-vector minus the vector differential operator of that scalar field. The scalar field is just a scalar field, just a one scalar, so we don't have a 4-vector equivalent of that. Okay, maybe some properties. It's anti-symmetric, and we can use these properties to prove what we need to prove. As see, it's sort of a huge monster with 16 components, but I said we only have six independent components: the X, E, X, Y, E, Z, and the B's. So this is only 6 independent components. Of course, these are complicated functions of space, 3 dimensions, and time. This is an interesting one, which comes up the inner product, the downstairs version of the tensor and the upstairs version. They yield this constant, minus 2 times the electric field strength squared divided by c squared, minus the magnetic field strength squared. The determinant yields a similar number, the square of the vector dot product of B and E. The trace, well, we can see that trace is 0 and so forth. So there's a lot of mathematical gimmicks there. But remember, basically, this electromagnetic tensor is is the real thing, and it shouldn't change. And that's yeah, what I show. I haven't I see I haven't sort of summarized the main argument. You can look it up. Any case, take it from me, this electromagnetic field tensor does not change when we change the gauge. Now, the interesting question for which I give these lectures is sort of like, it must be related to charge conservation, right? Local and global. And is it sort of easy to directly say, like, yeah, because we have this charge conservation law, which, as you know, we seem to drop a little bit when we go to these non-conservative, weak, strong forces and talk about color charges, which may pop up and not pop up and be borrowed. I don't know what. We don't have that in electromagnetic theory, and so we would be interesting to answer this question: like, is this gauge invariance? Can we show mathematically that it's just linked to the charge conservation law? The interesting thing, and some kind of natural, is where you say charge conservation alone, locally and global, the two together, do not imply or explain a gauge invariance of the of electromagnetics. We have just this whole play and spiel of indeed energy conservation as well, the energy in the field. the energy and the motion of the charges, kinetic energy, and that plays a role as well. So it's a whole and fully a complete system out of which the gauge invariance is more or less a consequence rather than a root cause. Now, I've been talking for a while, and I will now go to the most interesting question, I think, and that's this one. So it's a further reading will lead you to a more interesting question, and that is, you know, we in quantum electrodynamics, we work with wave functions, wave equations, which combine the laws of electromagnetism and the quantization that is inherent in nature. Energy is quantized, linear, angular momentum, and you know, we get these very interesting analyses in terms of wave functions. So what would change if we do a gauge transformation on the wave function? Do we get like new wave functions, or are wave functions unique? So we have a particle. I prefer to talk about, I will speak about it in a moment, the wave function of a charge. But does it change? Well, a priori you say, well, the physics shouldn't change, right? If they do, then your wave functions don't make sense. So yeah, that's true, and I will talk about. I will tell you in advance. The physics don't change, indeed, and I will tell you exactly how. The first is, though, the argument is very general that Aitchison Hey. I like to talk about the specifics of the situation. Are we talking about a particle or a charge in? Yeah, are we talking about a particle or a mere naked charge? What are we modeling exactly? I said, for me, electrons and protons even have a structure, so it's kind of difficult to fit that into, well, it's easy to fit it into a wave function, but it's something different, talking vaguely about a particle that moves in space or a mere naked charge. Are we talking about a charge? Yeah, we're talking about a charge. And if we are talking about charge, we're talking in free space, or is it a charge in an electron, an atomic or a molecule orbital, in a radial or a more complex electrostatic field with a nucleus or more nucleus when it's a atomic molecule. Then we also sort of we know there's a lot of discussion on which wave equation should we use. Schrödinger's. Schrödinger is not relativistic. I think that's a wrong perception. I will talk about that. Klein-Gordon, Dirac's, etc. The discussion goes on and on and on. So here I'm gonna show, though, my paper, where say basically if you think about wave functions, sort of the content. Wave functions are real. The problem is that you know, we think in terms of linear oscillations, and we should think about orbital oscillations. I'm not going to go into it too much, but here I show a lot of things, the real interpretation of the wave function, and I refer for the details of what I'm going to explain now to Annex 1. Where is it? Man, that paper is long. Here. Annex 1, the wave equations for matter particles in free space, which is the first I'm going to discuss. Let me go back to my notes. So Schrödinger's equation in free space, which we can write in a number of ways. We can bring, but it's basically that, you know, the time rate of change of your wave function, which is a function, of course, of x, the space vector, and t. Yeah, if I put it as a vector, is equal to the imaginary unit, which we know basically models, you know, I would say sort of a perpetual multibobulated, a rotation. I is a rotation operator. Times, but that gives us also a repeating, repetitive, periodic function. It's like a cosine or a sine, but a bit more complicated. It gives us the I is essential to give us a periodic function. Wave functions are periodic functions. Times Planck's quantum of action reduced times this very enigmatic 2 times the efficient mass, but the efficient mass because derivation Feynman originally is sort of for, you know, an electron that bounces from atom to atom, from electron to orbital, and acquires a bit of, you know, charge that acquires an effective mass because of the kinetic energy it has. My theory is that the 1/2 is there because a situation like that, you have kinetic energy and you have potential energy, and the energy partition theorem says that, you know, an electron, if you think of it as having some structure, the kinetic energy inside of the point-like charge inside and the electromagnetic field that keeps it into place, well, these two energies are make up both 1/2 of the total energy of the electron. So that's my interpretation, that 2 times the effective mass is the mass of the electron, and that's something that, you know, is treated being very, you know, confusedly by Feynman himself. Certainly he says, you know, the effective mass of our electron that we've been modeling in the context of a critical lattice becomes the total mass of an electron in free space. I refer to my paper for a deeper discussion on that. It's not very important. Thing is, the 2 factor, this 1/2 factor, does pop up in Schrödinger's equation for the electron orbitals in a hydrogen atom. And there my theory is a bit, yeah, of course it's there because we have electron pairs, and what Schrödinger's equation is modeling, what is the wave equation for electron orbitals. So we know that electron orbitals will preferably you know, have a spin up and a spin down electron, and so I think that explains the factor 2. You may agree, disagree. I can advise you to read my interpretation of that interpretation, but that's sort of how the thing looks like. We recognize this here, right? The E has been brought to the other side. You know, 1 divided by I is minus I, so that works. But the extra term that we have here is V, and it's a bit confusing. The V is not a potential, it's a potential energy. And potential energy are 2 different things, different physical dimension. Is the potential energy of the electron, of the 2 or the electron pair, in the electrostatic field of the proton. And I write that here, V as a definition. It's not this, well, potential has only a Q and has an R, but it's the electron charge squared divided by this factor that we know, the Coulomb factor, times, and it decreases as this is the inverse, not the inverse square rule, but it decreases with 1/r. Okay, Aitchison and Hey are going to prove what I want to prove now. What is the impact of a gauge transformation on the wave function? So I put the full general case where we have indeed electrostatic, well, electrodynamic fields. We have varying electric and magnetic fields. So we have also varying vector and scalar potentials. This is Feynman's general expression in the very last chapter of this volume 3, and it's the same as I mean, you can look at it for a while. He writes it all out with 2 factors here. Aitchison and Hey simplify this by using a bit of operator logic here. Yeah, this operating on the wave function, and it's a much nicer and simpler expression. You will say not so simple. Again, we have the enigmatic 2 times the mass factor. I'm not going to fight over that. Said, according to me, that's a bit of a misinterpretation between, you know, the distinction is not being made between an electron and a naked charge. For me, an electron has a structure, and the energy comes from the orbital motion, or non-orbital, but clearly it stays, it whizzes around and around, and that gives the electron its mass or energy, and half of it is in the kinetic energy of that point-like charge, which we get from you know, the anomaly and the magnetic moment, Compton scattering. There's a lot of you know, experimental evidence that says, you know, an electron is basically you know, it has a structure, and it's yeah, it's empty, and unless you hit, well, it's not empty. It's a whizzing point-like charge with a little dimension given by the fine structure constant that generates the electromagnetic field that keeps it in place. That sounds a bit crazy. Now, what's the point? Again, what we want to do, and that's what Aitchison and Hey do, we refer for this expression. If we take this expression and then we sort of link it to Maxwell's equation. It's a complex argument, 506. We can introduce two new operators which help with this proof, but it can then be shown that if we transform the gauge in exactly this way, the impact on the wave function, wave equation, through the wave equation, because if we change the gauge, then we have the scalar and vector potential here. Vector potential, scalar potential. Then you'll get a new wave equation. Yeah, well, a new one or not so new one, we need to see. But you will surely get new wave functions, and they will be equal, and that's what he shows. The only difference between the old and the new wave equation is that we have a sort of, I would say, a random phase shift, but it's a phase difference, a constant phase difference for all the solutions we get out of our new wave equation that we build up, that we get when we switch to a new vector and a new scalar potential. So you will say, well, what does it mean, a phase difference? Well, we know that that's a probability, and we don't know the initial condition. We don't know where the point-like charge inside of an electron is, so we don't have the initial conditions. And so basically a wave function that is different from another wave function just by this fixed constant phase difference, well, it's the same physics. And that's why they say QED, quantum electrodynamics, is gauge invariant, and that's the quantum ist demonstrandum, the mathematical proof of the gauge invariance of quantum electrodynamics. You will say we worked here with this wave function that you like, and most quantum physicists don't like Schrödinger's equation because it says non-relativistic. I said I refer to that paper here to show that I think that's a misinterpretation. I think it is dynamically correct and relativistically correct. But so yeah, they repeat the argument actually for other wave equations like Klein-Gordon, and they obtain the same results. That you change the vector and the scalar potential according to these rules, of course, so that the real physics don't change, and you will get the same results. You will find you need to adapt your wave equation, and then the wave functions you get out of it are different from the old wave functions just by this constant phase difference, and this is a delta, which is equal to Q times He, this scalar field. For the physical interpretation of that, I don't know how large is it, but it makes sense. We don't get different physics from our new wave functions. It's the same physics, and that's good, because otherwise those wave equations would not make sense at all. So that's it. I hope this was not too confusing. I have been talking for an hour, which is a lot, but it's less than I thought. I thought I would need like 2 hours to walk you through this. Don't hesitate to to like this video and comment on it. But yeah, as this video is quite technical, I would also appreciate quite technical comments, of course, not sort of simple ridicule like doesn't make sense. Comments like I often get. That's it. I wish you a really nice weekend. Maybe a while before I put another video online because I'm gonna go on holiday. But this is sort of one I wanted to put here, also to address myself a bit to mainstream physicists who sort of doubt that the formalism of QED. I don't quite get it. I think I do get it, and yeah, let's see. This is a video that basically goes over some mainstream logic, which makes sense, but I also point out at which points it clashes a bit with what I think would be a common sense interpretation for quantum electrodynamics, rather than talking about it in very mysterious terms. I'm gonna leave it at that. Really, Aitchison Hey are great also because of Aharonov Bohm effect and other things that I have talked about in my blog, which also aren't like the kind of weird stuff It's like the anomaly in the magnetic moment. Once you have a model, once you think, charged particles have a structure, once you think about models like Schrödinger's model for the nucleus, a Platzwechsel model rather than a strong force that keeps a proton and a neutron together. Once you sort of inject some common sense logic, and you distinguish between a particle and really go think through the Breuil's concept of matter wave, I would say. Electrons, protons having a structure, charged oscillations in 2 dimensions and 3 dimensions. This stuff becomes less messy, and as Feynman said, you will see it's not as bad as it looks at first.